Cool. So I apologize in advance because this is a very practical talk. Normally we do like a 4-hour workshop with this kind of content. So I've tried to compress it down. So if somebody wants access to the apps that I'm going to demo, and there's like longer slides and a longer recording, like it's more relaxed. If you see this is too fast, you can go to 7security.com free. And that's all. And there's also the vulnerable application that I demoed yesterday on the Lightning talk is also there for free available. So just to mention that. So I'm the CEO of 7security. We deliver training at Black Hat USA and so on. We do stuff with Cure 53 if you are familiar with them. And I'm one of the project leaders for OWASP OWTF. So if you type owtf.org, that takes you to the OWASP project, which is about web security. So some of the apps that I'm going to talk about today, especially Smart Sheriff, which was mandated in the entire country of South Korea. There's a couple of public pen test reports, so this is a very good way to learn about security. So just for free, by reading these first 2 pen test reports, you can pretty much see like a bunch of things that you should never do in a mobile application. So yeah, I'll talk more about that later, and there's a bunch of other mobile pen test reports available for free. So we will start with XSS, and then mobile apps with local servers, what can go wrong with deep links, some interesting scenario that we found in a pen test with a deep link SQL injection and code execution, and then some tales of crypto fail, and some API pwnage and so on. So let's get started, right? So XSS, web views and data exfiltration. Let's start with Android. So basically, on a mobile application, a web view is kind of a small browser. And of course, this can have HTML, JavaScript, and so on. So what is the potential, right? So we can have HTML injection, which in a mobile device can still be interesting because a mobile device, a mobile application is typically not going to show the URL to the user. So with only HTML injection, if you can craft a believable login page that sends credentials to an attacker, you can still do some pretty good damage there, right? Then XSS gets more interesting, and the scenario that I'm going to talk about is data exfiltration of local files using XSS, right? And then in some scenarios, you could even do cross-site request forgery as well, but that is kind of more rare. So we found this vulnerability in many mobile applications, but for the purposes of demonstrating it in a demo, without blaming the guilty, we modified an open source project that is called AndroGoat. So the official version will not work for this, but we modified it as part of the workshop where, using the modified version, this attack works, right? So basically, first we have to create some files on the application that we are going to steal later, right? So we go to insecurity test storage. This will make more sense in the demo. Share preferences, right? So we create like some, we save some data on the preferences, like my secret user, my secret password, in a SQLite database, the same thing. And then we can go to XSS, and we can start like trying some stuff, right? So we can try, for example, H1 hello. And you see that hello is kind of bigger, so that's kind of exciting. It means that there's probably HTML injection there. Then we can try some XSS payloads, right? Image source X, honor alert 1, script alert 1, and so on. So this demonstrates that we have XSS. And now the next question is, well, what is the context in which this XSS is running, right? So we know that with alert location. So in this case, we have, in the pop-up, we can see that it says file, right? So the URL is a file URL. So this means that there is no same origin policy. So we should be able to read local files if the web view is incorrectly configured or configured with weaker security settings, right? So in this modified version, there's 2 possible attacks. One is on internal storage, which is the data directory, so other applications cannot read this. And then the other one is on the SD card, right? So the SD card is interesting because it's kind of the Wild West of Android. So any application can read and write there as well. So you could have a malicious application on the phone that inserts something on the HTML from the SD card, and then when the victim application loads this, then you get XSS. So this would be another scenario, right? So first we have to find the paths of the files that we want to steal, right? So we have users.xml, and we have AGOT, which is the database. So the payloads look like this, right? So we send an XML HTTP request for the XML file, and then we alert it, right? So if the alert shows the contents of the file, this means we can also send this file to an attacker-controlled website, so we can steal local files, and we have this data exfiltration with XSS. And the same thing with the SQLite database, right? My throat is not very good today. So you can see there we have the alert of the user credentials, the password, and so on, and then the same with the SQLite database, right? So in the SD card, I already explained this. And then you can also like read files from the phone, right? So as long as the application can read the files, has permissions to read the files, you can read files like, for example, the phone configuration or even files from other applications, as long as the permissions of the file allow you to read this, right? So this is how that would look. The device here is a Xiaomi device, so this is the configuration from the phone, and then the SQLite database is to the right? So methodology-wise, you're trying to answer these questions like alert 1, we have XSS, alert location, is it a file URL? And then try to read the local files, but we need to know the location for this, right? So in Android, you need to have certain insecure settings in modern versions of Android, right? So before, this used to be like the default, but this was only up to Android 4. And now the developer kind of has to shoot himself in the foot to do this, right? So you need to have JavaScript enabled, and now universal access from file URLs, and so on, right? So, and also you need a file URL. So let's show this in a demo. So we are sending here the payload, and you can see that we can see the credentials for the user in the alert, right? So we can read an XML file. This is the SQLite database that we can also read. And now we will try the other files as well, right? So basically, you can just copy the payloads from a URL and then just try that, right? So now it's reading a file from Traversal. This is the file from the phone, right? So the Xiaomi device, and then this is from Traversal, so another application on the phone, which is loading a library that other applications can read. So yeah, so that's the demo. So. Now let's look at iOS, because of course this is also possible in iOS, and actually iOS had worse default than Android's up to iOS 13, right, which is fairly recent. So for this, we will demonstrate this using Dumb Vulnerable in CSRF version 2. So it has some web view issues exercise, and then we can try the same thing, like try hello with H1, and so on, right? So we are trying to answer the same questions. Do we get the alert 1? What is the URL? So in this case, we have an Apple web data URL, which is equivalent to a file URL. So we can also read local files like cellular usage and so on from the phone. So methodology-wise, we're trying to answer the same questions. Do we have the alert 1? Do we have the alert location? Can we read local files by knowing the paths? And so on, right? So this is the vulnerable code, right? So it's loading an HTML string. This is Swift code, so which is kind of weird because normally you would expect the double quote to be concatenated, you know, like to be like, you would expect like a second double quote to break the string, but in Swift you don't have to do that. You like do like this backslash, and then you have the name in parentheses, and this is concatenating the name input into the string. And then the other component that we have here is the URL is null, right? So there's an empty URL, so this means by default, the web view is going to load this with kind of maximal permissions without same origin policy and so on, so we can read local files, right? So that is the problem. And this is the default for UI web views. So web views, UI web views by default have WebKit allow universal access from file URLs and WebKit allow file access from file URLs. These are turned on by default and you cannot even disable JavaScript. So these web views are vulnerable by default to this kind of attack. But I think now in iOS 14, like Apple started giving developers warnings about this. So you need to use the WK web view if you are a mobile developer, and then you should be much better by default, right? But you can also shoot yourself in the foot by enabling these insecure settings. So yeah, it's about concatenating user input into the strings. So let's do a demo for this one. So we are trying first the alert one, right? So we get the alert one, so this confirms we have XSS. Now we have to do the alert location to figure out what is the security context in which this is being executed, this XSS. So this tells us that is Apple Web Data URL. So we should get excited because this means there's potential for data exfiltration. And now we will try to read some local files as well. So this is reading the data usage, and there's other known paths in iOS for certain files, right? So yeah, so you can see that you can read SQLite databases and so on. So as long as you know the path on the phone for the file, you are good to go, right? So yeah. So that's the demo. So now let's see some attacks on using the SD card on Android, right? So the SD card is dangerous location in Android for several reasons. One is any application can write there or read from there. So if you save anything sensitive on the SD card, a malicious application could read it. And then another problem is even a regular thief without elite skills can take the SD card out without even knowing the unlock pattern, plug this SD card into a computer and read everything in there, right? So by default, there's no encryption. You can take it out without even knowing the unlock pattern and so on. So yeah, kind of a memory problem. And yeah, let's see some scenario of saving sensitive stuff in the SD card, right? So this was a whistleblower application meant to be used in countries where they have kind of this oppressive kind of government and trying to let citizens report human rights violations. Unfortunately, this application was saving the human rights violation reports that people were entering in the SD card. So this could get somebody killed in a country like that, right? So you have police stop you, then they get the SD card out, they plug it into a computer, they see that you are reporting these human rights violations, and maybe they kill you, they send you to prison or whatever, right? So this could end up pretty badly, and this was all the data from the human rights violation report. Another scenario, what happens if you read data from the SD card, right? So this was an application loading text files from the SD card. So in this case, we have persistent XSS with data exfiltration, right? So we have a chapter text file being loaded from the SD card, and this is stored in a page data variable, and then the page data variable is concatenated into a string in HTML. So we have HTML injection and XSS. And then now for this, it's very useful to use hack vector, which is now also a burp plugin. So you can use eval from charcode if you have trouble with some characters that are breaking the application or whatever. And this kind of makes it a little bit easier sometimes, right? So this turns the payload that is retrieving the file into eval, string from charcode, and so on, right? So you get rid of the single quotes, double quotes, and it's more likely to work. So yeah, this was the persistent XSS with data exfiltration. And yeah, so Now let's see spoofing attacks, right? So in this case, you can use, for example, one URL to a user, but then when the user clicks on this, they really go to another URL, right? So a trick for this is to use left to right and right to left characters. So this has been used in the wild, and it can be an interesting attack vector, especially when the application linkifies automatically, right? So you can, for example, send some right to left characters, and then you put like mock.evil.org, and then when the victim really sees grow.live.com, but then when they click on it, they go to mock.evil.org, right? So they go to the reverse, right? So this can be an interesting vector. And then something that you would normally not think about is like a mobile application can sometimes have a local server, right? So it's kind of crazy, but possible, right? And then you have to worry about authentication, authorization, and so on. So this was a Cordova iOS application that was running a local server. So it had path traversal without authorization, so you could, by knowing the port, like a malicious application on the same phone could browse fast, right? So you could do this // of sequence of this, and then it's the password and so on. So you could read like local files and so on by using this local server, right? So this is a vector that normally you would not think about in mobile security, right? So you could like dump all the files like this, just in a shell one-liner and so on, right? So question for the audience: does cross-site request forgery exist in mobile apps? What do you think? Any takers? Cross-site request forgery exists in mobile apps? Yes, no? Maybe show up of hands, yes? Okay, so some people say yes, no. Okay, so yes. So cross-site request forgery exists in mobile apps, and especially with deep links, right? So this has it's a popular vector for like bug bounty stuff and so on. So I'm going to go a little bit fast for this because I want to cover other stuff later. But the slides are meant for like people trying to follow the exercises with the slides, right? But basically, in Android, you're going to have some deep link activity. This can be browsable or not. If it's browsable, then it's more exciting because it can be attacked from the browser also. If it's not browsable, then only a malicious application installed on the same device will be able to attack it. So we have one possibility is that the deep link activity has an intent filter, and then the intent filter defines the structure of the deep link. This is not necessary, but it's often like the way in which this is implemented, right? So I'll show other examples afterwards. So in this case, we have an Android scheme of some app, host of getcreds, and path prefix of user. So this is kind of the structure of the deep link that the application expects, right? So for this, I'm going to show a case study of cross-site request forgery using deep links on Periscope. So we have like the vulnerable version as part of the workshop that I mentioned before. So basically, first you need to create a Periscope account, and then we look at the Android manifest. With APK tool, you can decompile it. And then we can see that there's some browsable activities, and we can see the activity that we're interested in has a scheme of PSCP and a host of user. So what can we do with that, right? So we can send an ADB command, for example, sending Android intent action view, and then with the D, we pass like the intent data of PSCP user and then the ID of some user, right? And you can do this as well with Drowser and from a browser, so I'll show all methods. Also, with Drowser, there's a scanner, so you can scan for browsable activities, but this scanner is not super reliable, so it's going to miss some combinations, right? So you shouldn't rely on it. This is the output from Drowser. And then the actual cross-site request forgery vulnerability is that you can send a deep link that is going to automatically follow any user that you send to the victim without any confirmation from the user, right? So this is the actual vulnerability. So before we were just opening the profile, but when we add the /follow, The issue was you could like make the victim follow any user you want, right? So there's several ways to test this. One is with Deep Link Tester, which is an application on Google Play, and then you can send the, like type any deep link, and then click on go to URI, and then you can see that the user starts being followed. And the same with ADB. So ADB is what I normally prefer in pentest because every developer knows about ADB. So we can add the /follow there, and we can do the same with Traversal, right? So these are all the main ways, and also from a malicious website, right? So this is also available on this website. So you can also test it from there. And yeah, so if you just click on Periscope cross-request forgery demo, then it starts like following the user as well. So this is the HTML, and I'm just going to show the demo. So first it's going with Deep Link Tester, and it's going to follow the user. So it goes to URI. You can see that it changed to following, and then you have like to unfollow and close the user so that it follows again, right? So now we're going to do it with ADB. So you just send the intent with ADB, right? So ADB shell and so on. And we add the /follow. And then when you open the device again, so here I was like missing some quote. So yeah. And then you can see that it changed to following, right? And then we can do the same thing with Traversal. So we first have to unfollow, we close the user, and then you just go to Traversal and add the /follow at the end. And then this changes to following as well, right? And then from a malicious website, you can just go to this link. It says, requires no authentication or anything, and then you just unfollow, and then open the browser, and just click in there. And because the activity is browsable, the deep link arrives there, right? So I'm just explaining how deep links work, and now we will show other examples, right? So yeah, we need to go deep, right? So we're going to see more deep link scenarios now. So now let's see some deep link attacks to make phone calls. So in this exercise, we will use the vulnerable insecure app, but this is also a problem that happens like in real applications, right? But this is just for demonstration purposes as part of the workshop. So first in iOS, you look for URL schemes. So in Android, we were looking at the Android manifest. In iOS, we look at the info plist, right? So this is kind of the equivalent. And then in this case, we have done vulnerable insecure app and done vulnerable insecure Swift. So these are the two URL schemes. If you have Xcode, you can look at this by looking at the project, info, and then scrolling down to URL types, and then you have URL schemes, right? So this is how that looks. And then we know how the deep link starts, but to know what the application does with this deep link, we have to look at the source code, right? So that's the easiest way. So that is going to be done in the app delegate. If the application is written in Swift, this will be appdelegate.swift. If it is written in Objective-C, it will be appdelegate.m, right? So this can vary, but this is, in this case, this is the logic for this. So it's looking for phone call number, and it's going to split this into an array called split URL, and then it's going to cast, if you're familiar with PHP, this would be the equivalent of explode, and if you're familiar with Python, this would be the equivalent of split. So basically, it's taking a string, looks for phone call number, and then it's going to explode this into chunks, right? So the chunk 0 is going to be the deep link, and chunk 1 is going to be the phone number, right? So then it casts the phone number to an integer, and if this works, it assumes it's a valid phone number, and it tries to make the call, right? So yeah, if you look at Xcode, this is how the code looks there. And Based on this, we know now the structure of the deep link, and we can demonstrate from a malicious web page, right? That the user clicks like win an iPad now, and then it makes a premium phone call. So this is an interesting attack vector on mobile applications to monetize the attack, because by making the user ring a premium phone number, you can make money basically as a criminal, right? So this is these are the deep links. It's basically just a web page with links to the deep links, and then the only thing Safari tells you is open this in the vulnerable insecure version 2, and then you just tap on open, but you don't really see the link, right? So here we're showing the link because this is just for demonstration purposes, but in a real attack this would say win an iPad now or something like that, right? So yeah, so let's do the demo for this one, so that you see it working. So basically, you just click on the link, and it's going to make the premium phone call, right? So you tap on open, and then it says success, and it's just simulating that it's making the phone call, right? And the same with the other URL handler, because there's two, right? So it does the same thing. Okay, so with that, now that we know what deep links are about, let's see some scenarios from the field. So one possibility is that you have an application that is a browser application, right? So you have a URL, and then this URL has to be opened by the browser. Now, if you have a malicious application on the phone, what you can do is to save something on the SD card, and then make the browser go to this location on the SD card, and then try to read local files, right? So this is the scenario, right? So this is, in this case, the deep link works in a slightly different way. So in this case, we don't have an intent filter that tells us the structure of the deep link. This is actually done in the code that is looking for this search query. So it's slightly different than the example I showed before. And then we can make the application go to the SD card and steal databases, because its URL validation actually accepts file URLs, which is really bad, right? So yesterday in my demo for hacking Electron applications, there was also a remote code execution because the user would click on a file URL, right? So file URLs, both in mobile and desktop applications, very interesting always. So yeah, this is very interesting. And basically what you do, this is like the attacker code, right? So you specify an HTML file on the SD card, because all applications that have SD card permissions can read and write there. And then you just send the intent to the browser application and make it go to the HTML file. And then once the browser application goes to this HTML file, you can try to read local files, right? So this was all the data exfiltration, retrieving all the databases from the application, and then sending them to an attacker, right? So we have a deep link, and then XSS with data exfiltration, right? So we are combining the concepts that I explained before. Yeah, and then now let's look at another scenario. So this is a browser application that goes to an attacker website that attacks the deep links, right? So this is a slightly different approach. So in this case, this was the Onion browser, one of the early versions in iOS. And what we could do is, from an attacker-controlled website, we can call the deep link from the application and do Onion browser force quit. So if you showed an image like this, the browser would automatically close without any user interaction, right? So you can invoke functionality in the application by using deep links, right? So this is also an interesting vector. Now, another very cool attack is a deep link that results in SQL injection and then results in code execution, right? So this was a very cool vulnerability. So this happened in a CRM application with Google authentication. So when the user tries to use the app, you get prompted to log in with Google. So there's like a pop-up, and then the user logs to Google, and then the credentials go back to the application using a deep link that sends the Google token, right? So that is the idea of the implementation, and this is the code. So we have, in the Android manifest, we have the login web view activity. You can see it's browsable, so it can be attacked from the browser as well. And the scheme We will call it a vulnerable app to protect the guilty. And then in the code, you can see that there's database db.execute SQL, update credentials, set call, and then there's a concatenation of the value, right? So we have SQL injection. And then the question is, how can we turn this into code execution? So it turns out in SQLite, when you use the SQL Cipher extension, then you can load extensions as well from SQL, right? So in this case, we can do select, load extension, and load a library that we know the location of on the phone to get the code execution firing, right? So there's two potential scenarios. One would be a malicious application, so we can simulate this by going to, for example, data, just trust me, and then we create a test.so file that has a lot of A's, and then we give it permissions with chmod 777, so any application on the phone can read this, and then we send the intent that exploits the SQL injection, loading the extension that we know the location of on the phone, right? So this was the error on logcat, so you can see it says SQL Cipher DL open failed, has bad elf magic. So it's trying to execute it, but it sees that it's not a valid binary, but this is enough proof to know that this is code execution, right? Because it's trying to run it. So yeah, this is remote code execution, so always exciting. And then also in supported versions of the application, this was also exploitable from a browser. Now, because you need to provide the library to load to turn it into code execution, this was a little bit tricky, right? So we need to take the user to an attacker control website, and then this website has to make the user download the binary and then run it, right? So we need first one file that is just going to send the binary to the user. So we're basically doing test.so, and then it's just having a lot of A's. And then we need to load this in an iframe. So when the user visits this, it will automatically download. And then we wait like 5 seconds or something so that there's enough time for the binary to download. And then we exploit the SQL injection and get the code execution, right? So, and then we have the same error message in logcat, right? So this was pretty cool. Now let's talk about URL validation, right? So this was the logic of the application. So this was the Onion browser again. And in this case, it's trying to check that, because the problem is, if you have a .onion domain, then this domain is not following the normal TLS trust process, right? So it works in a different way. So it's trying to skip SSL errors, right, if it has .onion. But there's a problem here, because this is actually a very common problem when you do code audits, because it's just looking for .onion somewhere, not .onion at the end of the host name, right? So yeah, this is going to ignore all the warnings, and we demonstrate the vulnerability like this, right? So we created a subdomain like www.paypal.com.onion.something else, the domain we own, and then we make it point to a Google IP address. So when you visit that domain from a normal browser, you would get security warnings. But when you visit it from the Onion browser, there were no warnings, right? So this is a very common problem when you do code audits and the user does, the developer does something like if string in, if this string appears somewhere, instead of maybe they should be checking the start or the end, right? So very common problem. If you do code auditing, you really need to always look at this because there's always interesting bugs. So yeah, now XMPP is also an interesting protocol because lots of chat applications use this, right? If you man in the middle XMPP, you will notice that in the handshake at the beginning, it's possible to specify the mechanism, right? So you can specify, because you are the man in the middle, that the only mechanism available is plain, right? Because normally there's like a challenge response. So if you specify that the mechanism is plain, then the user credentials, if the application is dumb enough to trust this, will be sent in clear text, right? So they are provided base64 encoded, but you can basically base64 decode, and then you can read them, right? So this was also a nice attack. Also, attacking updaters, an interesting attack vector as well. So in this case, it was an application getting a JSON file from the server. So we can, because it was doing this over clear text HTTP, we can change the URL and specify a phone number as the place to get the update from. So then the application says new version available, and then you tap on update, and it makes the premium phone call, right? So these are interesting attack vectors in mobile when you can make the user click on something that makes a phone call. Things can get interesting, right? So it's an interesting vector to bear in mind. Another one was a third-party zip file retrieval. So in iOS, since iOS 9, there's this thing called app transport security that makes applications reject clear text HTTP traffic by default, but developers can add exceptions to this, right? So you should always look at the info plist for things like this, because if developers have an exception there, it's typically for a reason, that they need to make a clear text HTTP request to that URL for some reason. So in this case, it was an Amazon S3 domain, and this was the request looked something like this. So you can see it's a clear text HTTP retrieval of a zip file. So we have an arbitrary file overwrite, because if we can provide any zip file we want, when the application unzips it, we can overwrite any file we want on the application. So also a cool vector. Now let's talk a little bit about crypto. So a crypto messenger Android application. Can anybody see the vulnerability there? Any guesses? It's on the line that's highlighted. So the problem is the original file name, right? So whenever an application respects the original file name on the file system, things can get interesting, right? So in this case, we have an arbitrary file overwrite on decryption, because a user sends an encrypted file to another, and then when you decrypt the file will be decrypted with the original file name provided by the user, and there's no sanitization here or anything. So you could encrypt a message with an original file name of .. something, and then when the user decrypts the file, you can do an arbitrary file overwrite of whatever, right? Now PGP, this was a PHP email iOS application. So just going to skip this because, so basically at the bottom you can see there's a string concatenation on the message, right? So it says string escaped for JavaScript, but it was not escaped for JavaScript. So this is the actual vulnerability in the first line. So you can see self-message string escape for JavaScript, and there's a string concatenation in the JavaScript. So you could send an email to another user that had like a single quote, semicolon, and then the XSS payload. And then because the application is in the JavaScript, you can see it's doing first like the private key, the passphrase, and then the message, right? So by the point the XSS fires, the private key and the passphrase are already set in JavaScript variables. So when the XSS fires, we can just send the private key and the passphrase to an attacker-controlled website by the email. So this was also a very cool vulnerability. And then, yeah, the attacker can just receive this, right? So yeah, if you don't have private keys, they can't be stolen, right? So that's also interesting to bear in mind. So now let's talk a little bit an application very close to my heart that was mandated in the entire country of South Korea. So by law, every parent and child of this country was forced to install this application. This is true. And the idea was to keep the children safe, help parents be parents, and so on, right? So the pentest reports are public, so you can read more about it there. So the first time we tested them, everything was clear text HTTP, everything everywhere, right? So this was the first round, no SSL. What is SSL? No SSL anywhere, right? So all HTTP. And this is also quite common in Asian applications. And I don't know why, but it's what we found, right? So the second time, we noticed, okay, all URLs are HTTPS. So it seems like they fixed it, so that's nice. But then we looked at the validation of SSL. So this is what the validation looked like. On received SSL error, proceed. So if there's any SSL error, it's just going to proceed anyway. And then the second line, hostname verifier, that's all the code, return true. So all the hosts are good, and all the SSL errors are good, right? So basically, so we have from clear text HTTP and then to completely broken SSL, and then they were doing this crypto stuff with XOR. Now, there's nothing wrong with XOR. XOR can be very secure if you use a one-time path, for example. However, in a mobile application, if the mobile application has the hard-coded, the key of the encryption hard-coded in the binary, anybody can retrieve it, right, by reversing the binary. So the first problem was there was a hard-coded XOR key, which could be retrieved. So we wrote this Python script with a hard-coded key to do the encryption and decryption and so on. And then this was the actual key. So they were like using this to encrypt the phone numbers in the HTTP request. And then in the second round, they added this AES layer, which was also using a hard-coded key like somewhere else on the phone, right? So this was the code, right? So by reversing the binary, you could get both the AES key and the XOR key. So this is completely like useless crypto, right? So because anybody can read the key. So at the end of the day, there's nothing wrong with AES, there's nothing wrong with XOR, but if the keys can be retrieved by the attacker, all the crypto is useless, right? So a key distribution problem. So the catastrophe summary is you have a phone number, then it's this encrypted with XOR, which is completely useless because anybody can retrieve the XOR key from the binary. Then the entire request is encrypted with AES, which is also a useless encryption layer because the AES key is also hard-coded in the binary. And then the request is sent to the server, but as we saw before, it's completely ignoring all SSL warnings. So this was the fail SSL. And then you get the response back from the server, right? So it was a complete disaster implementation. And yeah, let's talk a little bit about API attacks because then it would not, this talk would not be complete with this. So this is a path traversal. So typical, the developer tries to change ... to nothing. So this is wrong because you can provide ... like twice, and then ... turns into ... so you're back to the same place, right? So the attacker, instead of sending ... a bunch of times an empty password, by sending this, you still can get the traversal, right? So this is a very well-known trick. Another case is a remote code execution in a file upload, Python using shell true, concatenating the command, and so on. So we could get like a reverse shell like this. So we have like to encode different parts of the requests and so on. And then we got like a reverse shell back. And the server was already running as root, so no privilege escalation required. That's always nice. And yeah, so yeah, that's about that. And now let's talk about API leaks, right? So this is about the smart sheriff and stuff. So there was a sister. Okay, no. So first there's the bully API. Let me see in 2 minutes if I can finish this. So in every classroom, there's always this child that is a bully, right? That he wants to mess or make the life of every other children in the class miserable. You've all probably know some person like this, right? So for this child, if he wants to make the life of some child miserable, the first thing to ask the API is, hey, I want to mess with this child, right? I know his phone number, and I really want to screw his life. What can you do? And then you ask the smart sheriff, this Korean application that I was talking about before. It asks the smart sheriff API, and then the smart sheriff API tells you, okay, for that phone number, this is the parent phone number. So now you can already do some damage there as a bully kid, like you can call the parent for pranking purposes or whatever. But as a bully kid, you need the password as well of the parent, right? Because the parent phone number is cool, but to log in, you also need the parent password, right? So you could ask politely, right? In life, you should always ask questions. The only thing that can happen is maybe you don't get the answer you were hoping for, but when you ask questions, amazing things happen, right? And this is a very good example of this, right? So you ask the API, please, smart sheriff, help me, I want to log in as the parent of this child. And smart sheriff, of course, gives you the password of the parent as well, encrypted with XOR, as we saw before, with the hard-coded key. So completely useless encryption layer. And with that, you could log in as the parent of any child in the classroom, and then you can say, well, this child cannot access any website, can never use the phone, cannot have any applications installed on the phone, right? Because that's what the application was for. And this is what the requests look like in practice. So you send the message request, and then you get back the parent mobile and the PIN, right? So because this application was mandated in the entire country of South Korea, you could try a lot of phone numbers at random and get all the passwords and so on. And then there's Smart Dream, which was a cousin application of this that was looking for harmful words used between children. So for example, if a child sends another child a message that contains the word sex, then it would count that as a harmful word, and then this message would be saved in the API server. Right? So the problem was you could see the message of any child that had been flagged with some harmful word, and yeah, so this was all very bad. So I'm going to skip this one. So I'll show just the password one. So this is like trying random phone numbers in Korea, and then it tells you if it's the parent or the child. If it's the child, it tells you the parent phone number, and then from the parent phone number, you also get the password, and it was just trying the random phone numbers like this, right? So that's that, and then I'll show the Smart Sheriff. So, and this is the Smart Dream, which is the custom application. So it's telling you like all the messages and from what phone number it was, and then what the messages were. Now, this script was written by Fabian, and he replaced the Korean characters with random characters, so to protect the privacy of the people. But this is basically what it looked, right? So, violence, assault, it's like you also get like the category, and then the phone number that sent the message and the actual content of the message, right? So I think that's all the time I have. And yeah, so any questions? Or maybe I'll show another demo while we wait for the questions. So this like Smart Sheriff stuff was so bad that the pentest report was indexed by Google. So we reported also an XSS, and the XSS was indexed by Google, so you could like click on the link, and the XSS was still working. So it's like really funny, like you screw so bad that the pentest report is public, you report some XSS, the Google indexes your vulnerabilities, and you can like click on the Google result and get the XSS firing, right? So this whole like Korean application was like catastrophic. Okay, so sorry. So time for questions.
Well, first of all, thank you very much, Abraham. I think people are hungry, and there's no questions that came in. I don't know if we have any questions that we want to take in the audience with the microphone. Otherwise, I think people are starting to get hungry and want to go eat. And maybe they will grab you during lunch hour.
Sure, feel free.